am Cindy Croson. I'm a professor of biostatistics and medicine at Mayo Clinic. Today I'm going to explain survival analysis, which is one of the most commonly used methods in orthopedics research. Survival analysis is also known as time-to-event analysis. Time-to-event data occur commonly in orthopedics research, and these data require analyses using survival analysis methods. Survival analysis is not only used in analysis of patient survival or time to death, but all types of events that occur during follow-up. In survival analysis, we want to estimate the occurrence rate of an event that occurs after study entry. In orthopedics, study entry is typically surgery, and the most common events of interest or outcomes in orthopedics are complications or revision surgery. Survival analysis data are complex because both a follow-up time and an event indicator are needed to correctly describe the occurrence of the outcome of interest. Time-to-event data occur in any study design involving longitudinal data, both retrospective and prospective observational studies or randomized clinical trials. Retrospective studies may identify patients over a period of time, and prospective studies often enroll patients over a period of time, such as 1995 to 2014, and then follow them until they die, their last medical visit, the end of the study or last date of data collection, or a chosen end date for the study. So the data often looks like this, where each subject has a primary total joint arthroplasty on a different day, and they are all followed for different lengths of time. Then if they have an event, such as a revision surgery, those are marked with an X. Patients without the event may not all be followed until the same date, based on when the last information on each subject is known. Then for analysis, we usually reorient the time to the time since study entry scale, with all patients starting at time 0. In this example, we collected data on 20 patients to see whether they had revision surgery or died over the course of 20 years. As you can see, the patient at the top of the graph had a revision surgery about 1 year after the initial surgery. So survival data is really a type of incomplete data where we have complete information on those that had an event, but we don't have complete information on those that still had not experienced the event at last follow-up. We haven't had a chance to observe them long enough, or maybe they never will get the event if the event is something other than death. All we really know is that we have observed them for some time, like 243 days, and they have not yet had the event. We call these censored. We might think of analyzing these data as a binary outcome using perhaps logistic regression. This analysis would be appropriate when every patient is followed for the same length of time. This is possible with short-term outcomes, such as 30-day surgical complications. However, when the follow-up time is not the same for all patients, logistic regression is inappropriate because it does not correctly account for the length of time that each patient was followed. So we need special methods to analyze time-to-event data. It is also incorrect to report raw percentages of events, like 10% of patients had a post-surgical complication, when all the patients are not followed for the same length of time. The event rate depends on the length of follow-up, and it should be recorded at specific times, such as the complication rate was 1% at 30 days and 2% at 90 days. It is also incorrect to show a table of patient characteristics with columns for event and non-event, such as no infection and infection, or no revision and revision, when patients are not followed for the same length of time. Also, it is incorrect to perform two-sample tests to compare the columns of these tables. Those who are followed for a shorter amount of time may move from the non-event to the event group if followed longer. For time to event data, we often use the Kaplan-Meier method to estimate the event rates. Here we use the data from our hypothetical set of 20 patients. This list of numbers is a shorthand we use that will be used throughout this talk to summarize time to event data. This says there's an event at time 1, which is the top patient on the graph. There's an event at time 2 and a censor at time 2, which are patients 5 and 7 on the graph. And then an event at time 3, 2 censors at time 4, and so forth. At time 1, the survival probability is 19 divided by 20 because you have one death at time 1 and everyone else is still under observation. So that is easy, 95% of patients survive. Then at time 2, we take the 95% from time 1 and we multiply it by 18/19 because there are 19 people left and one of those dies. That calculation yields 90%. So here's the whole table of calculations. We have the 95% from time 1 and the 90% from time 2. We go on to the next event at time 3 and we take the 90% times 16/17. Then at time 4, there are 2 censors and there is no calculation. There are only calculations at times when there are events, but we do reduce the number of patients under observation when those 2 patients finish their follow-up. So the other thing you notice here is that if there is an event and a censor at the same time, we consider that the censored person was still under observation when the event occurred. The censors fall out between that time and the next time. Here's the Kaplan-Meier curve for these data. You've probably seen these in the literature. Sometimes the censors will be marked as they are here, and sometimes they won't be. The steps indicate where events occur, as the survival probability changes when events occur. You can tell by the step size roughly how many people are under observation, as the steps get larger toward the end of the time scale when there are fewer patients under observation. A large step could also result from multiple events on the same day, as noted by the bigger step at time 8 where there are 2 events. It's important to understand censoring patterns to avoid potential bias in a study. Most of the time-to-event methods assume non-informative censoring. So when someone is censored, the idea is that patients remaining under observation at that time could stand in for the censored subject from that time forward. You expect that if you were able to follow the censored person longer, what would happen to them is similar to what actually happened to the people that you were able to follow longer. Informative censoring should be avoided when possible because it almost always leads to biased estimates of the event rates. If a patient's medical record ends because the patient is too sick to return or the patient has died, this is informative censoring. Censoring a patient who has died during follow-up will also lead to biased estimates of event rates. This topic is covered in another video on competing risk analysis. If follow-up involves a survey, patients who are too ill may be less likely to respond to a survey. Informative censoring also may occur in the data collection process. For example, if an investigator continues to track events of interest, but does not update follow-up for patients without events. When some patients in the study are followed differently from others, there may be informative censoring. How do you identify censoring problems? Identification of potential problems related to censoring requires careful review of study procedures and the data. For example, in a prospective surveillance study after surgery, is it possible the patient did not return for a follow-up visit because the patient has died? If so, does the study have procedures in place for collecting death information, or is data only collected at the follow-up visits? Comparing the characteristics of patients who did and did not return for a follow-up visit may also identify problems related to informative censoring. A more complex approach to error detection is to perform a Cox model analysis with the event and sensor indicator switched in order to consider censoring as if it were an event. This analysis can reveal characteristics associated with censoring patterns. In conclusion, time-to-event data in orthopedics requires survival analysis methods, and survival analysis should be used more often in orthopedic research. The most common errors encountered in analyzing such data include methods designed for binary outcomes and failing to recognize informative censoring. In the next module, we will discuss how to compare two Kaplan-Meier curves, and we will discuss Cox proportional hazard models, which can be used for more complicated comparisons.